Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last couple of lectures of ECE3400 analog electronics, we computed some equivalent circuits for looking in various terminals of bipolar junction transistors. We computed a Norton equivalent for looking in the collector of the BJT. We computed a Thevenin equivalent for looking into the base of a BJT. And in this lecture, we'll complete the trilogy and compute a Thevenin equivalent for looking into the emitter of a BJT. Now, I realize that all of this material seems fairly abstract and esoteric, but trust me, it will pay tremendous dividends in terms of simplifying the kinds of analysis we can do when looking at various amplifier structures. As in the previous couple of lectures, the BJT symbol here doesn't represent a BJT in its full glory. It specifically represents a small signal model. So according to our convention, all of the voltages and the currents here are indicated with lowercase letters. So you can do this analysis using the T model or the pi model. As with the previous two lectures, I'll do this analysis with the pi model. You can do the analysis with the T model and move back and forth between the results you get using the two models, using some other known relationships we've derived. So I'm going to compute a Thevenin equivalent looking up into the emitter of the BJT in terms of a Thevenin equivalent computed looking out of the base of the BJT. Now, in terms of what's happening out here at the collector, we can remain agnostic about that. The circuit is doing whatever it's doing up here. So we'll express the Thevenin equivalent in terms of a Thevenin resistance and a Thevenin voltage associated with looking out of the base. So let's take this Thevenin equivalent looking out of the base and paste it onto our pi model. So as we did in the last lecture when we computed a Thevenin equivalent looking into the base, we're going to use the R0 approximation. So we're going to assume that this resistance R0 in our small signal model is infinite, so it essentially goes away, and this drastically simplifies our analysis. All right, so now to compute a Thevenin equivalent looking up into the emitter here, the traditional way to do this would be to first compute an open circuit voltage, and then you would zero out the independent sources, and then you would either fix IE here and then compute VE in terms of IE, or you would fix VE and then compute IE in terms of VE, and then you would divide those quantities to get a Thevenin resistance. Here, like with the base computation that we did in the previous lecture, instead of going through all that formalism, I'm just going to write down a KVL equation for this loop here and hope that a Thevenin equivalent looking thing magically pops out. It could happen. All right, so we can say that the voltage at the emitter here is the voltage associated with this Thevenin equivalent for the base, minus whatever voltage is lost across this series combination of resistances, RTB, and our small signal input resistance, R pi. And here I can write that down according to Ohm's law by multiplying by this current IB. Now, I really want a relationship that relates VE and IE. So if we recall from one of the previous lectures, we have the relationship that this IE prime equals IB times 1 plus beta. And if you'll recall, the IE prime is something that we developed for the case where R0 isn't assumed to be infinite. In that particular case, we made this distinction between IE and IE prime. But because we're using that R0 approximation here, I can get rid of the prime here, and then I can divide both sides here by 1 plus beta and replace this IB here with IE over 1 plus beta. And then if I look at this, I say, oh, I have a constant voltage, and then I have something in the form of Ohm's law, so that looks kind of like a Thevenin equivalent. So let me define RIE to equal this business here, this RTB plus R pi divided by 1 plus beta, allowing me to rewrite this as VE equals VTB minus IE times RIE. And then I can write down a circuit that looks like this that just implements this equation. So my Thevenin voltage is just VTB. My Thevenin resistance is RIE. So I can take all of the mess up here and replace it with this simple looking circuit. Now, there's another way I could write RIE. In a previous lecture, we found that RE, which is a quantity associated with the T model, is equal to alpha over beta times R pi, which is associated with the pi model here. And if I rearrange this expression, let's remember that alpha is equal to beta over beta plus 1. And then if I plug that in for alpha here, the betas cancel, and I can write RE as R pi over 1 plus beta, which is sitting right here. So I could write this as RTB over 1 plus beta plus RE. Now, if I had worked out this Thevenin equivalent from the beginning using the T model instead of the pi model, I would have derived this formula here. And then I could use this relationship to derive this formula. So you can use one or the other, whichever is more convenient in any given circumstance. This Thevenin equivalent circuit for looking into the emitter gives us a new way to interpret our Norton equivalent looking into the collector that we computed a couple of lectures ago, because we can take all of these stuff up here and replace it with that Thevenin equivalent. So if I do that, I can write a circuit that looks like this. So here I've used this Thevenin equivalent looking into the emitter to replace all of these stuff up here. Now I can easily find the emitter current as being the difference of these Thevenin voltages looking out of the various terminals. So I have my VTB and my VTE here, divided by this series resistance, RIE plus RTE. Now I'm thinking about a Norton equivalent for looking into the collector, so I really want things in terms of the collector current. And let me copy those formulas for RIE down here. Now here we really want an expression in terms of IC because we're thinking about a Norton equivalent looking down into the collector. So our Norton short circuit current can be related to our emitter current by just multiplying by alpha. Now I want to caution you that this is only because we're using that R0 approximation. If we weren't, then we would get primes involved in this formula, and our overall analysis would be a whole lot more complicated. So I can take my expression for IE, substitute it in here, and write something like this. So let me take this expression here and copy it onto the next slide. Let me define a capital GM. So I can then write our short circuit current as GM times this difference between the Thevenin equivalent voltages looking out of the base and the emitter. And this should now look very familiar. This GM here is equivalent to all of the GMs we computed in that initial lecture about looking for a Norton equivalent circuit for looking into the collector. And it's also equivalent to this formula we computed in the last lecture when we were dealing with equivalent circuits looking into the base. So we now have not 1, not 2, not 3, not 4, but 5 equivalent formulas for this GM quantity. So let's once again go to Marshall Leach's ECE3050 website. Remember, 3050 is an earlier name for what's now called 3400, and we'll click on the BJT formula sheet. So in the first lecture in this series, we computed a Norton equivalent circuit looking into the collector. In the second, we computed a Thevenin equivalent circuit looking into the base. And here we see that there are 2 Thevenin equivalent circuits for looking up into the emitter. One of them with this RE prime looks up into the part of the small signal model that doesn't have R0. The part here with this RIE includes the R0. Now, in this particular lecture, we've used the R0 approximation, so these two models are actually the same. And if we scroll all the way down to the bottom here in the R0 approximation portion of the formulas, we see this RIE equal RIE prime. Now, if you don't like the R0 approximation, Marshall has all these formulas here for using R0 in its full R0 glory, but they are quite messy. They don't provide a lot of intuition as to what's going on, and I'm not going to use them in this class. For a perspective on how we use these things, remember that the collector can only really act as an output. You never think about the collector as being an input. Similarly, you never think about the base as an output. You only think about the base as an input. The emitter, on the other hand, might be considered an input or an output depending on the circuit. And in some situations, you can consider it kind of a combination of an input and an output. We'll talk about that later in the class. So we use this kind of Thevenin equivalent circuit when we're computing the gain and the output impedance of the common collector configuration, aka the emitter follower, and when computing the input impedance of the common base configuration. Now, if you really want to see where these messy formulas with R0 in its full R0 glory come from, you can go to Marshall's 3050 website, and if you scroll past 2010 and scroll all the way down to 2006, if you look up in the write-ups he has here, you'll see BJT Norton collector, Thevenin base, Thevenin emitter. If you look at these, you'll see where he goes through all of the details, including R0. But it gets pretty messy, so I'm not going to worry about that here. But it's there if you're interested. The last thing I'll mention here is that if you go to Marshall's main website and scroll down a little bit, you'll see this link for selected publications. And one of the publications here is called On the Application of Thevenin and Norton Equivalent Circuits and Signal Flow Graphs to the Small Signal Analysis of Active Circuits. And this is the place in IEEE Transactions on Circuits and Systems where he published this particular approach to analyzing small signal circuits using Norton and Thevenin equivalents. So you don't have to read this paper, but it is pretty awesome, and it's here if you're interested.